Okay, thank you. It's really nice to be back at KITP. My talk has worked on this preprint from last October with Umang Mehta, Chintan Patel, Karthik Sharma, and Shiroman Prakash, and touches on earlier work. Okay, so this is an outline to the talk. So let's start. As all of you know, S-matrices are among the best studied and most interesting observables in quantum field theories. Now, S-matrices are best understood in so-called trivially gapped theories, theories with no massless particles, and which in addition flow at low energies to empty theories, theories that are not, have no content in them. Okay, in such theories, many things we understand many things about S-matrices. To start with, S-matrices have an identity piece, which is just nothing happening, plus I times an analytic function. And that analytic function is believed to obey the property of crossing symmetry. This is the statement that if you know particle-particle scattering, you can figure out what particle-antiparticle scattering is by interchanging initial and final states and complex conjugating representations. Okay, for 2 to 2 and 2 to 3 scattering in such theories, in fact, crossing symmetry is a proved property of such theories. In contrast to these theories with these trivially gapped theories, these theories with no massless particles and that are trivial in the IR, theories with massless particles are more complicated. The S-matrices in such theories can be less well behaved. For instance, in an extreme case, in conformal field theories, it's widely believed that S-matrices just don't make sense because you make a particle and then it keeps showering and that process never stops. Okay, we will have nothing to say about S-matrices and theories with massless particles in this talk. Now, there's a class of theories that's somewhere in between these two extremes. There's a class of theories that's somewhere in between these two extremes. These are theories which have no massless particles, but are not trivial in the IR. Are theories that reduce in the IR to topological field theories rather than trivial field theories. In such theories, because there are no massless particles, there isn't a continuum of states going down to the vacuum. One might expect that the infrared divergences that sometimes plague S-matrices with massless theories don't exist. However, these theories are not quite empty in the IR, so you might expect that the long-distance properties of these S-matrices are different in these theories compared to the most familiar trivial theories. Okay, in this talk, I will try to argue that this is indeed the case. I will try to do this in the context of a particular example. The example I study is a theory in which at low energies reduces to the poster boy of topological field theories, namely Chern-Simons theories in 2+1 dimensions. And the theory is a gapped, genuine quantum field theory. It has real degrees of freedom, unlike pure Chern-Simons theories, local degrees of freedom, unlike pure Chern-Simons theories, but reduces at low energies to pure Chern-Simons theories. It's very easy to make such theories. All you do is to take pure Chern-Simons theory and couple the theory minimally to massive matter. Below the mass scale of the matter, you've got pure Chern-Simons theory. Above the mass scale of the matter, you've got a genuine quantum field theory with stuff that can scatter. And the question we're going to ask is, what are the structural properties of scattering matrices in such theories? Okay, now, the reason we've chosen these theories to study is that a lot is known about these theories. These theories have been studied intensively over the last 15 years or so. In a particular large N, large K limit for theories involving fundamental matter, turns out these theories are solvable. And the exact solution of these theories, a lot has been exactly solved in these theories. In particular, the S-matrix of these large N, large K theories with fundamental matter have been computed. And from the explicit computational results for the S-matrices, one finds the following. Okay, so even in order to tell you what one finds, I have to introduce some technicalities. We're looking at the scattering in a theory where particles are always either the fundamental or anti-fundamental of, let's say, SUN. So there are two inequivalent types of scattering processes in such theories. Fundamentals can scatter against each other, or fundamentals can scatter against anti-fundamentals. These are qualitatively distinct. Now, if two fundamentals scatter, they can scatter in a channel in which the fundamentals couple to either the symmetric or the antisymmetric of the gauge group. If a fundamental scatters against an anti-fundamental, it can scatter in a channel in which the fundamental fuses with the anti-fundamental to form either the adjoint or the singlet of the gauge group. Okay. Now, crossing symmetry tells you that if you know fundamental scattering, you can deduce from that what fundamental anti-fundamental scattering is. And if you work out the rules for what you might expect, and I'll review those rules in a moment. If you work out the rules for what you might expect, you get a certain prediction for the adjoint and singlet scattering matrices in terms of the fundamental scattering matrices in this symmetric and anti-symmetric channel. You compare these rules against explicit results. You find that the adjoint scattering matrix obeys this, what you expect, but the singlet scattering matrix does not. There are two surprises in the singlet scattering matrix. This is what you would naively expect from analytic continuation from the fundamental scattering. You get that times a factor. So that's surprise number one. Surprise number two is that it's multiplied by some number times a delta function that's supported only on forward scattering. Okay? I'm going to try to explain in this talk both these features to you. Okay. So let's start with the second feature, the delta function, this cos pi lambda minus 1 times forward scattering delta function. Okay, let's try to understand why this term comes about. Let's look at two particle to two particle scattering. Let's work in something like the center of mass frame. Okay, in such a frame, we're working sort of relative coordinates. There's an incident plane wave in relative coordinates incident on a scattering center. We're working in a theory which has no massless particles. So the part of the plane wave that is far enough away from the scattering center in units of 1 over the mass just does nothing, just goes straight through. That part makes the part that's identity. Okay? A small part of the wave, a finite part of the wave, that's within a radius of 1 by the mass of the scattering center, scatters. That part makes the tau. So we have identity plus I times tau. Okay? Now, and one can argue in these theories, quite generally using, for instance, a partial wave expansion, that this tau is an analytic function. Now, let's now take this discussion and specialize it to 2 plus 1 dimensions. In 2 plus 1 dimensions, the cross section of this plane wave that's coming at you is a line. Okay? And the scattering center breaks up this line into 2 disconnected components. That wouldn't have been true in any higher dimension. Okay. So, if we've got some trivial theory, once again the parts of this wave that are far away from the scattering center just goes through. Nothing happens, they produce identity. But what if you've got a non-trivial theory, a theory with which has non-trivial physics, a topological field theory in the IR? Well, in this case what happens is the following. Locally, this guy just goes through, the guy up, and the guy at the bottom also goes through. But they pick up a relative phase with respect to each other. This phase is basically the Aronoff-Bohm phase. Okay? And you can write down a formula for that phase. You can the phase that it picks up is, for instance, you're choosing a particular gauge. The guy on the top picks up e to the power I pi nu. The guy at the bottom picks up e to the power minus I pi nu. Where 2 pi nu is given by the 2 pi times hr1 times hr2 minus hr. Where r1 is the representation of the, okay, so we've got these particle scattering in representations r1, r2 and r. R is the effective channel of scattering, for instance, singlet or adjoint. Okay, and hr is the chiral dimension of the operator in the related chiral 2-dimensional theory that is sort of dual to the Wilson line created by the particle in question, thought of in topological terms. Okay, so from the point of view of the low energy theory, every particle is some sort of Wilson line. That Wilson line has is an operator in a dual chiral conformal field theory. HR is the dimension of that operator. Okay, so now because the guy at the top picks up this factor e to the power I pi nu, the guy at the bottom picks up this factor e to the power minus I pi nu, when what would have been half plus up plus top plus bottom becomes half times e to the power I pi nu plus e to the power minus I pi nu, and therefore cos pi nu. Okay? And so instead of scattering being 1 plus something analytic, scattering turns into cos pi nu plus something analytic. If you set up the formalism of scattering that doesn't know about this, what you find is, you set up a formalism of scattering that assumes the scattering matrix is 1 plus something. It will kick back and tell you that something has a 1 minus cos pi nu times a delta function. Okay? And so that is the explanation. That is the explanation for this piece here. Okay. Now, the explanation for this was already in some less sophisticated version was already in our paper from almost 8 years ago. The main point of today's talk is to explain the other feature, namely this factor. What's the deal with this factor? Again, in our paper 8 years ago, we tried to sketch some sort of explanation and was more or less on the right track, but was not very precise, not precise enough to get a prediction for theories at finite n and k, for instance. The point of today's talk is to give you a clear argument, clear explanation for that factor, clear enough to give a prediction for what happens at finite n and k. Okay, where we cannot do the calculation explicitly. Okay. Okay. So let's start. So to start with, I'm going to start with some trivial group theory. Okay. Suppose that our particles that are scattering are in representations R1 to, okay. Suppose I'm doing scattering in, let's say, SUN theory. And consider a collection of representations of SUN theory in representations R1 up to Rn plus m. Okay? If I have a tensor that lives in this product representation space, I call it an invariant tensor. If I'm rotating the tensor, I get back the same tensor. Okay. Now, given an invariant tensor, I can use that to construct an S-matrix that commutes with the SUN, the SUN symmetry. So for this part, for these 3 slides, imagine we're dealing with a theory with a global symmetry rather than a gate symmetry. Okay, imagine that SUN is a global symmetry. Okay, so I can construct an S-matrix that is SUN invariant by contracting that invariant tensor with bras and kets, and here this gives you an S-matrix which maps the initial Hilbert space RA1 to RAN to the final Hilbert space RAN plus 1 star to RAN plus M star. The star is because some of these are bras and some are kets. Okay, and this S-matrix is invariant is G invariant because T was an invariant tensor. Okay, now I took an invariant tensor and used it to make an S-matrix that scattered R1 to Rm and then Rm plus 1 star to Rm plus n star. I could have made the division somewhere else. Okay, I could have split up the indices of that tensor somewhere else, and that would then have parametrized another scattering process with different initial particles and different final particles. Okay, the claim of classical crossing symmetry is that the S-matrices defined by the same invariant tensor are related to each other under analytic continuation. Okay, so that's how crossing symmetry works with global symmetry indices. Okay, now 1 or 2 quick trivialities about theories with global symmetries. It's nice to think of these S-matrices, the group structure part of these S-matrices, entirely in terms of these invariant tensors. Now, sometimes we need to multiply 2 S-matrices together, or more precisely multiply an S-matrix with its dagger. We need to do this in order to study unitarity. So, this multiplication process, what does it mean in terms of these invariant tensors? If you think about it for a moment, you will realize that taking the dagger of an S-matrix is just complex conjugating the invariant tensor, including all representations. So fundamental becomes anti-fundamental. And multiplying S with S dagger amounts to taking these 2 tensors and contracting away the multiplied indices, all indices corresponding to the final particles. Okay, so you can form, in terms of these invariant tensors, crossing is trivial, and the rules for crossing, for unitarity, which involves multiplication of S matrices, are easily formulated. Okay, so multiplication is just contraction, basically. Okay, now, in order to explicate the rules for unitarity in theories with a global symmetry, it's nice to sometimes work to use a particular basis for these invariant tensors. Okay, So one can do that as follows. Suppose I take my initial particle state space RA1 to RAN. I can decompose that into irreducible representations of the gauge group. Let's say SUN. That any given irreducible representation may occur many times. So A is a multiplicity. A is which representation, and there may be a multiplicity index which runs from 1 to QA. Okay. Now, what we do is to work with orthogonal states in every particular representation we get. Okay, that's this formula there, and define these invariant tensors, or more precisely the maps that correspond to the invariant tensors, by taking an orthogonal state in representation A with another orthogonal state in representation A made out of the final particles. Okay, so these are the initial particles, these are the final particles. There's some multiplicity index R and R prime. You multiply and sum over all the internal indices, okay, all the JZ indices. This quantity is group invariant, sort of manifestly, and gives you a basis for the space of invariant maps or invariant tensors in group space. Okay, so if we work with this, so these quantities I'm going to call projectors. They're labeled by which representation we project onto, and then two degeneracy indices. Okay, if we work with these projectors have some nice properties. For instance, it's easy to check that if you multiply a projector with a dagger, you get a third projector. Oh, there's a delta R4 R2 missing here on that formula. There's a delta R4 R2 times another projector. So projector times projector gives you projectors with some delta functions in representation space. Also, if you have a projector going from one space to itself, then the sum over projectors sort of diagonal in this degeneracy space gives you identity. Okay, these are easy things to check. It would take you 2 minutes if you sat down with paper. Okay, since these projectors are a basis for the set of our group invariants, we can take S matrices and expand them as S matrix with projector indices times the projector. Projector labels times the projector. And then using all those properties up there, you can take the formula of unitarity, S dagger is equal to 1, and ask what it means for these S, A, R prime coefficients of the projectors. And you find that what you get is basically that SARR prime times SARR prime is equal to S. So just S, convolution S is equal to S. The only complication being that these guys are matrices in degeneracy space, and they multiply by matrix multiplication also in degeneracy space. Okay, and become identity also in degeneracy space. Okay, so in this basis, the rules for unitarity are just small deformations of the usual rules for unitarity. In particular, if there's no degeneracy, the coefficient S matrices just obey the standard formulas. S convolution S star is equal to 1. Okay, now it's these standardly normalized S matrices that we will try to keep track of. We'll try to keep track of the standardly normalized S matrices properties under crossing symmetry. Okay, so let's see how this works in context of an example. Suppose we're doing 2 fundamental to 2 anti-fundamental, or 2 fundamental to 2 fundamental scattering. We're looking at S matrices with the insertion of 2 fundamentals and 2 anti-fundamentals. A basis of invariant tensors in this space is, just some random basis is given by contracting the fundamental and anti-fundamental indices in the 2 possible ways. That's TD and TE. The Hermitian conjugates of these tensors are given as follows, just a complex conjugate, which means switch fundamental and anti-fundamental. Okay, in terms of this random basis, we can construct the projectors onto the symmetric and anti-symmetric representations. We can check that all the properties that we expect for projectors work, that TA times TS, for instance, is 0. Okay, similarly, we can do that for the identity, the singlet and the adjoint, check all properties work. Then we write down the S matrices as S matrices times these projectors in each of these 2 channels. And just by using the rule that I told you about, that is, S matrices corresponding to the same invariant tensors continue to each other, we then compute the rules for crossing symmetry, and this is what you find. This thing here. This is the expectation that we had when we did these calculations with these matter-Chern-Simons theories. This is the expectation that doesn't work out correctly in these theories once you include the interaction with Chern-Simons theory. Okay, great. Now that we have the setup, let's move to the scattering of Chern-Simons theories coupled to matter. Okay, these S-matrices of Chern-Simons theories coupled to matter can be pulled out if you know the transition amplitudes between an initial state and a final state. Now, a transition amplitude between an initial state and a final state is a path integral as a function of initial and final boundary conditions. If we're computing such a path integral, in these matter-Chern-Simons theories, we can try to work this out in a world line representation. Okay, so we can do, okay, the first thing I should have said is that I'm working on a space-time in which the boundary of space, everything is regulated, but the boundary of space is taken to be very far compared to the length of time. Okay, so the pillbox which I've drawn long should actually have been drawn flat. Okay, because of that, nothing really happens at infinity. And because of that, infinity can be shrunk to nothing once we continue to Euclidean space. Okay, so this path integral here, which has some boundary degrees of freedom living here from the Chern-Simons point of view, the Hamiltonian for these boundary degrees of freedom is 0, because nothing reaches them. So they're doing nothing and they can be shrunk to a point. Okay, so the path integral, once we continue to Euclidean space, is effectively that of a ball, with half of the ball being the final and the other half of the ball being initial. Now we do a path integral in which we have to integrate over all gauge fields and matter fields. We turn the matter field path integral into a world line sort of representation. Okay? Once we've got a particular world line, we do the integral over the gauge fields. Now the integral over the gauge fields then gives us the expectation value of an open Wilson line in pure Chern-Simons theory. This expectation value is topologically invariant, and so it depends only on the topology of this world line. Okay? So in the end, we get an expression for this S matrix, which is of the form, we've got some S matrix, which depends on the topology of world lines, times a Wilson line that is parametrized only by topology. Okay? Now, of course, there are still an infinite number of topologies of world lines. However, Witten taught us that these kind of path integrals with open Wilson lines going from somewhere to somewhere on a boundary are actually conformal blocks. And the space of conformal blocks is finite. So we can take all of these different topologies and expand them in terms of conformal blocks. Okay, and so this expression that I had above, sum over topologies, turns into this expression, which is an S matrix, which is Si times Gi, where Gi is a conformal block. Conformal blocks are finite, and we're going to play the role that invariant index structures played in the previous, in the study of theories with global symmetries. Okay, so this is the structure of S matrices in these theories. S matrices are component S matrices multiplying conformal blocks. Okay, now, okay, as I mentioned, conformal blocks will play the same role in the scattering of matter-Chern-Simons theories that invariant index structures played in the scattering of theories with global symmetry. One nice thing about this fact is that when you take a conformal block, take the limit k goes to infinity, it turns into an invariant index structure. So it's like the finite k quantization of invariant index structures. Okay, now I want to formulate unitarity and crossing in terms of these component S matrices. There are two immediate questions. The first really important one is, how do we multiply two conformal blocks? What plays the role of the contraction of index structures for invariant tensors? And the second interesting question is, what is the block analog of the special projector invariant tensors that we constructed earlier? Now, if you think about this physically, what compounding of these blocks means, multiplication of these blocks, is very clear in the Wilson line representation. All you have to do is to fuse Wilson lines in the part that you are fusing, the final state part, and continue the Wilson lines. Okay, so from the Wilson line point of view, which is clear physically because the particles just keep moving, what is to be done is sort of clear. Okay, so we define a mathematical operation in pure Chern-Simons theories, which goes as follows. I've got some sort of, open Wilson line configuration, and to aid visualization, I take the part that I'm fusing, the final state part of it, and flatten it. Okay, so I've got two of these guys that I overturn one on top of the other, and also complex conjugate to change all representations to inverses, and then I just sit and glue. Okay, so this gives you a multiplication operation on conformal blocks that maps product of two conformal blocks to a third conformal block, possibly with different representations. Okay, this kind of multiplication operation was also considered by Witten in his classic work, except that what he did was fuse everything. That was his operation in which he considered the inner product on block space. What we're doing here is defining a halfway operation that takes us not to numbers but to two additional blocks. And physically, it's clear this is what we have to do. Okay. Now, there's a warning here. There's a technical warning which we don't have the time for, which is basically the multiplication rule is not a multiplication on blocks, but multiplication on blocks plus a sheet structure. Because Wilson line representations don't give you a block, but give you a block plus a choice of sheet structure. Anyway, all that we don't have the time for. Okay. Now that I know the rule for multiplication, I can ask, can I construct these projectors? The kind of invariant projectors that we had before. And the answer is yes. There's a very easy construction, and in fact one that was more or less contained in a paper by Witten, a follow-up paper to his classic paper in 1989, in which he studied Wilson lines like this. Okay, consider some representation R1 up to Rn. I don't know why I've done Rn plus 1. N minus 1. Anyway, R1 up to Rn. Okay, and you consider the Wilson line configuration you get by successively fusing these guys. Okay, finally you fuse it to some Ra. Okay, now this is some Wilson line, some block, and if you that's the analog of this M structure that we had. The projector was MM and is obtained by taking one of these and fusing the Ra to the other guy. Okay, this almost gives you the construction of the projectors. It turns out you have to do some normalization to these guys. In the context of an example, I will explain the normalization to you. Okay, but apart from a normalization, this gives you the projector construction. Okay, once you do the normalization correctly, you can show that these projectors obey exactly the same algebraic properties as the invariant projectors built out of invariant tensors that we had before. So that P dagger P is equal to P, that has G dagger G is equal to G, sum over, this should have been G, sum over, identity works just exactly the same as before. Okay, so now if we use these projector blocks as the basis for S-matrices, then because all the algebraic properties of these projector blocks are the same as the algebraic properties of the invariant index structures, the rules for unitarity for these SA, ARR prime are the same as before. Okay, so when we work out the rules for crossing symmetry for these SARR primes, we'll be working out rules for crossing symmetry for S-matrices that obey standard unitarity properties. Okay, now I'm going to show you how this works in an example. Okay, consider the scattering of two fundamentals with two anti-fundamentals. I'm going to now construct the projector blocks for the symmetric channel. So what we do is to take fundamental, a Wilson line, fuse to symmetric, anti-fundamental. That's basically what we have to do. The anti-symmetric block is this, but we need some normalization. Actually, before that, let me show you this orthogonality. The orthogonality is the statement that I take this and I compound it with that, I get 0. Now, that is the statement that this block is 0. Why is it 0? Well, just cut it along the dotted line. There you have a path integral with two insertions, two Wilson line insertions, one in the antisymmetric, one in the symmetric. That, according to Witten, is the 2-point block of a symmetric and an antisymmetric representation, which is 0, because 2-point blocks only are non-zero only with representation and their conjugate. Okay. On the other hand, if you do it with symmetric and symmetric, you get something non-zero. So there's a complex conjugate that I'm not talking about here. Okay, and you can compute what that non-zero thing is. The complex conjugate is contained in the arrow structure. Okay, and you can compute you get something non-zero. In fact, this non-zero thing is the same as this guy up to a number, because the space of two-point blocks is one-dimensional. Okay, and you can compute this number by taking Witten's inner product on both sides. and evaluate the number as the expectation value of this guy divided by this guy. And therefore, in the end, deduce that the symmetric and anti-symmetric projector blocks that are normalized are given by this expression. 1 minute left, yes. Okay, maybe I'll take 1 minute more. Okay, fine. So you can do the same thing with fundamental, anti-fundamental scattering. Okay, you can produce a singlet projector by appropriate normalization. I give you the final construction. This is the adjoint, the projector onto the adjoint, and this is the projector onto the singlet. Okay, now I've got these projector onto adjoint onto everything. In order to work out crossing symmetry, all I have to do is to take the decomposition in terms of S times projector 1, S1 times projector 1 plus S2 times projector 2, and rewrite that in terms of S1 prime times projector 1 prime plus S2 prime times projector 2 prime, the two different bases. The rewriting gives me some linear relation, that gives me the rules for crossing symmetry. Okay, now that rewriting can be done, okay, and there are some subtleties. I've on these slides explained the path integral manipulations you need to do to compute the coefficients. We don't have the time for it. So you can do it. I'm just going to the final answer. You can do it, and in the end, this is what you get. You get that the identity and the adjoint are related to symmetric and anti-symmetric, okay, by these relations. Now, if you compare with what we had early on in this talk where we were doing the classical stuff, the global symmetry stuff, we have the same expressions, except that that label Q was not there. Now, what does that label Q mean? The label Q has the following meaning. MQ is equal to Q to the power m by 2 minus Q to the power minus m by 2 divided by Q to the half minus Q to the power minus half. Okay, so MQ is a Q number M. And the famous properties of Q numbers include the obvious statement that in the limit Q goes to 1, a Q number reduces to the ordinary number. Q here was e to the power 2 pi I by kappa. Kappa was the shifted level, n plus k of this theory. So in the limit k goes to infinity, Q goes to 1, and this reduces to the classical scattering crossing symmetry rules. Okay, but when Q is not infinity, these rules are different. Okay, now let's look at what happens in the large n-thousandth limit where we had explicit computations. Okay, when we work out these rules in the large n-thousandth limit, this is just the classical thing who works out. When we work it out in the thousandth limit, this Q number is not trivial anymore, and you get identity gives you the sine pi lambda by pi lambda, precisely the factor we found by explicit computation, and the adjoint had no factor. Okay, so that disagrees with computations is non-trivial. Check. And now I've got some discussion telling you how important this work is. Okay, I'll stop. Okay.
Thanks for a great talk. First question to Shiraz.
So I guess in principle what you explained applies also to ADS3, like a Chern-Simon model theory put on ADS3. But in that context, I think it's more natural to have crossing symmetry intact.
Yes.
And so does it mean that there is a different normalization of the conformal block in which the you manifest the crossing symmetry but not unitarity?
Yeah. It's a great question. In fact, one I've been thinking about. Perhaps I don't have a clear answer yet. It's a great question. Something that's on my mind.
Why does crossing symmetry have?
Because he says that because in ordinary conformal field theories, let's take just a normal conformal field theory, something like ADS3 times S3 times T4. Okay, there we have Chern-Simon's terms in the bulk, and we expect these conformal field theories just to be usual standard vanilla theories. Yes. Of course, there are many issues there. There are gravitons in the bulk. There are various things to think about, but it's a great question, one I'm thinking.
Yeah, you don't have to give a very detailed answer, but I'm just curious. So when you do crossing symmetry, it's very important that you go to the upper half plane, not the lower half plane. So there's some kind of orientation choice there. Is there anything analogous to that in the vectors you manipulate? It's like you somehow sketch that you have to exchange some legs, like in your vectors. So how do you choose which way you swap them?
Yeah, you see, that kind of question. The detail of what is the path, this is the level that we've not looked at all. Okay. Right? What we're trying to do is formulate what we think is the right answer, And then the question of what path and can you do it from that path and so on is a next level. I would imagine you do the usual thing.
But could you see that one path is wrong and one is right?
Well, in the usual story, one path is wrong and one path is right, right? Yeah. So I would imagine it's the same thing here, but I have nothing further to say about that. Yeah.
More questions?
So at the beginning of this talk, you got this cosine -1 term for the singlet factor, but nothing for the adjoint.
Yes.
And you explained it via this phase. So is this phase trivial for the adjoint channel?
Yes. So in particular, not quite a phase, right? Because the sine pi lambda by pi lambda is not in the end of phase. But yes, so if you take this Q-deformed thing, and you take the large n, large K limit, you indeed get just 1 for the adjoint answer, but you get sine pi lambda by pi lambda for the singlet. So both work out.
Yeah, the other term is cosine -1.
That cosine -1 is also trivial. Yes. So in fact, that cosine -1 tells you the effective anionic phase in the scattering channel. Okay, and in all other 3 channels, it is either 1 over n or order 1 over n squared. Okay, the reason for this is something you know very well, that when you have Casimirs in a large n Chern-Simons theory, it just depends on the number of boxes, or number of boxes plus number of anti-boxes. So if you're doing fundamental, anti-fundamental scattering, in the adjoint channel, the number of boxes plus anti-boxes is conserved. So the H1 plus H2 minus H just cancels to leading order. Okay, but in the singlet channel, it's 2 initially and 0 finally. That's why it's not. Yes. Thank you.
People recently consider bounds on the couplings of theories where they write down an ansatz where crossing and analyticity are manifest, and then you impose unitarity.
Yes.
Let's say we want to bootstrap these theories.
Yes.
Can you write an ansatz which makes these crossing symmetries manifest?
Yes, that's this point. Yes. I think so. Sorry, maybe I haven't. First, the question of putting unitarity and crossing together. As you know, in order to do these dispersion relations, you need the crossing relation because you want the U channel in terms of the S channel. Right, so you need to input the crossing relations. Because these crossing relations are different, we're going to get a different set of constraints. And writing down these constraints, I think, if you believe my crossing relations, should be straightforward. Now, what was your question again, please?
I think I was thinking more in the direction of what Pedro and Joao are doing, where they're writing this raw ansatz, which makes crossing analyticity manifest, and then and I was just...
Interesting. I haven't thought about it. Interesting. I don't know their work in any detail. I would have to think. But one suggestion is this. We have very explicit answers in terms of large and large these theories. The large and large K, Toft limit. Looking at those answers might help you come up with an answer.
Right. Okay.
Yeah.
Thanks.
More questions? Is the upshot of the previous minute that maybe the way we normally do S-matrix bootstrap, we are missing certain types of theories, so we can't claim to...
Yeah, you're plugging rules for crossing symmetry into S-matrix bootstrap.
Yeah. So I mean, you're kind of identifying situations where that is insufficient for interesting...
Yeah, those rules would have to be modified. So you would have to change it. I should say that I think that though we've worked this out in the context of these Chern-Simons theories, at least in 2+1 dimensions, I think it's pretty clear that some version of what I say would apply to any theory which flows in the IR to a topological field theory. So basically, it seems to me that at least where people were working in theories with the mass gap, what's been done so far is valid for theories which are trivial in the IR. And maybe in 4 dimensions, for instance, it's not so easy to find examples of these other theories. But at least in 2+1 dimensions, they're very easy examples for theories which don't fall into the context of what's been done so far. You need to generalize, I would say. Not that I've done anything specific, but this is what I would guess. Yeah.
I mean, it's similar to Shota's question, but let me insist that you speculate a little bit.
Okay.
Will you have some edge modes, some degrees of freedom at the boundary?
Okay, let me say one thing that is relevant to Shota's question. Okay, that is this. You see, okay, I'm just going to write somewhere and half of the audience can't see what to do. We'll break the symmetry. Okay. We've got this kind of expression, right? This S is equal to SA times GA, where GA is some sort of block. Okay. Now, one thing that you know is the following. Let's suppose we had a conformal field theory, okay, where you had an expansion like some correlation function is GA bar times GA. This is how conformal field theories have built correlation functions that have normal standard properties. Like you've got a complex conjugate block times an ordinary block. This is how a conformal field theory is built, correlation functions that are single valued and that have many nice properties in 2D CFTs, right? That's what's presumably happening in the context that Shota is asking. Okay, now let's look at this guy here. One thing that's odd about these GAs is that they're not single valued in general. They're branch cuts. Okay? On the other hand, this S matrix here has no branch cuts. Okay? The S matrix has no branch cuts, and you can understand this in several ways. Okay, so what's happening here is that these SA functions have the inverse branch cuts compared to these GAs. So what I believe is going on is that these SAs are behaving like the GA bars. Okay, so that we've so far focused on the properties of these guys and not looked at these very much. Okay, these guys are going to have properties, for instance, which will make everything single valued, which will agree with Shota's expectations. This is my expectation for how it's working, but I understand it so poorly I'm not going to insist on it. But I could tell you a little bit more if you're interested. Oh, Jota.
More questions?
Now, the discussion that I gave you here was meant to be anything to anything. Okay? So at the level of my discussion, if you believe the discussion, it applies anything to anything. If you ask, what do we know explicitly at large N and large K? Nothing. Sachin Jain and collaborators have computed many S matrices in these theories basically at tree level. So there are some tree level expressions. But if you want all loop expressions, nothing is really known. It's sort of an interesting question. It's an interesting question connected to the following thing. You know, if you take a two-particle state, just non-relativist quantum mechanics, and you put these anionic boundary conditions, a two-particle state is the same as one-particle state because you can move to center of mass and relative coordinates. And then you can solve it by going to polar coordinates. Now, if you take a three-particle state, just in non-relativistic quantum mechanics, and put anionic phases, already I think that's a very hard problem.
Any more questions? Okay, let's thank Shiraz again.